Okay. All right, welcome those who are watching this video later on at home. Not all the problems will be available on this video. You will have to go to a second video to see the remainder questions. We'll see how far we get today though. So we're just gonna jump straight into it and we're just gonna work on this together, okay? So question number 1. The table below shows the age and favorite type of music of 668 randomly selected people. So as you can see, here's the age, and then here's the music type, and the breakdown is here. So we are given a two-way table. Use a 5% level of significance to test the claim that age and preferred music type are independent. Before I go any further, I want to ask you guys, of our 4 options, ANOVA, chi-squared goodness of fit, chi-square independence, and chi-square homogeneity, which of those 4 is this problem?
Independence.
Independence, good. So I'm just going to put that up here. So this is chi-square independence. And then you can use our toolkit table that we worked on today to help you continue if you wish. Part A, what are the null and alternative hypotheses? So the null is always going to be that the variables are what? Independent. And then the alternative will always be that the variables are what? Dependent. But make sure to put the variables in for the context of the problem. So what are the 2 variables in the context of this problem?
Age and music type.
Good. Age and music type. So we're going to say that music type and age are, one more time, what was it?
Independent.
Independent. Okay, independent always comes first. And then the alternative is that music type or music preference, however you phrase it, and age are dependent. Also, that order didn't matter. You could have put age first and then music type or music preference, up to you. Any questions there? Okay. Part B. Using your calculator, fill in the expected frequencies table below. Are the criteria for chi-square distribution met? Round to 3 decimal places. Okay, one thing at a time. Let's first get our expected values. To do so, you need to take the original observed data value from the two-way table and enter that into matrix A. So we're going to do second matrix. Go over to edit. I know you guys here in the classroom can't see my calculator, but if you watch this video later on, the calculator is on the iPad. So edit matrix A. Now remember, it has a number by a number, which is rows by columns. How many rows do we have? 3. How many columns do we have? 3. So you have a 3 by 3 matrix. If the totals were included in the observed data set, do you include the tables, the totals in your matrix? No. Very good. All right, so enter in your data. So 50, 85, 73, 68, 91, 60, 90, 74, and 77. Once you've entered in all of your data, you go to Stat, Test, and go up to chi-square test. Oops, I went too far. To chi-square test. You may have to hit enter a few times. But you should get then the chi-squared value of about 12.95, p-value of about 0.0115, degrees of freedom is 4. Again, I'm sorry you guys can't see it here in the classroom right now. It's on here, but I don't know why it's not appearing on there. But I will be rewriting these values. Okay. So actually, let's go ahead and do so. If you want to, hold this off for a second, okay? Let's come back to it, because at this point in time in our calculator, you should have chi-squared, the p-value, and degrees of freedom, which we can use to answer part C. It did not say where to round, so let's go to 3 decimal places. So the test statistic, chi-squared, was 12.954. Degrees of freedom was 4. And the p-value is 0.011. No, 0.012 once you round.
I'm getting something completely different.
Okay.
And,
Maybe double check your data values that you entered.
yeah, so I did it, right? And then it's changing it automatically to, every time I do it, it changes it to 2x4. I know, but I just put, this is the 3rd time I tried to put it in, and I just changed it.
3.
I did that, and
And
then
now do your numbers.
I did.
I forget what the numbers were. So they were 50, 85,
85.
73, 68, 91, 60, 90, 74, 77.
Okay.
Okay.
Now watch, now go.
Then you go to list, test. Do the chi-squared test. Read through it, and then there's your X and your P's and your degrees of freedom.
Yeah.
Yeah.
So be sure to hit enter all the way through the matrix. Perhaps if you entered in your last value but didn't actually hit enter on that very last value, it didn't recognize that the full matrix was entered in. That might have been it. Any other questions up to here, guys? Or anyone else need help with their calculators? Okay. Now, I skipped a part, right? Part B. We need it wants us to give the expected values. That way we can state whether the chi-squared distribution criteria have been met or not. So in your calculators, go back into matrix, so second matrix. You could just go straight to the name B, but I like to go to edit and then B, just because the formatting looks better in my opinion. So go to B, and you should get the following results. Let's say it says to round to, does it say to round? 3 decimal places. So 64.766. I'm going to go horizontally, okay, horizontally across. 77.844. 65.389. 68.192. 81.961. 68.847, 75.042, 90.195, and lastly, 75.763. Okay. So, are the criteria for chi-square distribution met?
Yes.
Yes. Why? Yeah, because all expected values or expected frequencies are greater than 5. All those values we just found are greater than 5 in our table. Okay. Any questions up to here? Yeah.
For the greater than 5, when would it be that we would say at least 5 or equal to, or is it always going to be greater?
It's going to be greater than 5, yeah. Part D, what conclusions can you make about the null and alternative hypothesis? Well, you take your p-value, let's convert it to a percent, Be careful here. I think this is where I see a lot of students make a little simple mistake. They move the decimal incorrectly. So remember, I move the decimal twice to the right. That's 1.2%. What was our level of significance? 5. So that's less than or equal to 5%. Is it statistically significant?
Yes.
Yeah. So statistically significant, which tells us to reject the null and support the alternative. Part E, state your conclusion in the context of the problem. So this is our overall conclusion now. So at the 5% significance level, the sample data support the claim being your alternative hypothesis, support the claim that music type or music preference and age are dependent, because that's what we said in our alternative hypothesis. We said that those two variables are dependent. Any questions? Yeah, so this is a really good example of chi-squared independence, right? Doing all the work out. Everyone feel okay? Are there any questions? Okay, you guys want to do another one? Definitely have time for another.
Please.
Okay. Number 2. A teacher figures that the final grades in the chemistry department proportions that are distributed as follows. 25% are A's, 25% B's, 40% are C's, 5% D's, and 5% F's. At the end of a randomly selected semester, the following number of grades are recorded for 160 students. So in the observed values of the sample are as follows. So let's stop, or actually wait, let me read this next sentence. Test the claim that the grade distribution for the semester is different from what is expected. Test at a 1% significance level. So let's stop here. Remember, of our 4 options, ANOVA, chi-square goodness of fit, chi-square independence, and chi-square homogeneity, which is it?
Goodness of fit.
Goodness of fit, good. So chi-square goodness of fit. All right. Part A, what are the null and alternative hypotheses? Well, the null, H naught, that's going to be each distribution that this chemistry teacher, this chemistry teacher is expecting, which was provided. They're right here. This is the distribution of grades that this teacher is starting off with that's expected. So just write those values out. So probability is 25% or 0.25. The second probability is 0.25. The third probability for C's is 0.40 or 0.4. For D's, it's 0.05. And then for F's, it's 0.05. Because that's what was given. And if you were to add those all up, that adds up to 1 as expected. Instead of P sub 1, P sub 2, P sub 3, P sub 4, P sub 5, if you chose to write it as P sub A, P sub B, P sub C, P sub D, P sub F, you could do that if you wanted to. Up to you.
Wait, why don't these have to be the same?
They don't. For goodness of fit, they don't. Only the ANOVA, they have to be the same. So for goodness of fit, they could all be the same. So how many are there? 1, 2, 3, 4, 5. They could have said that all the grade distributions are just all 0.20, or they're all equal, in which case it would be 0.20A, 0.20B, 0.20C, and so on. But they don't have to be. For goodness of fit, they could either all equal the same value, or they could all equal different values, just so long as it adds up to 1.
Oh, that matters that it equals 1.
Yeah. So then for the alternative, I'm going to say the grade distribution
We can't just say at least one population mean is different?
you can say something like that. Yeah, there's different ways of phrasing
I
this.
said at least one of the values stated in the null are different.
Yep, that's acceptable.
Okay.
Yep. So the grade distribution above, I'm going to say, is not all correct. Right? At least one of them is wrong. At least one of them is different. There's different ways of phrasing it, but just indicating that something's wrong here.
What then is?
Part B. Find the, or any questions there on the null and alternative? Okay, part B. Find the expected frequencies and fill in the table below. Are the criteria for chi-squared distribution met? Well, remind me, how do we find the expected frequencies? What's the formula?
N times P.
N times P, right? N times P, where N is the sample size, right? And P is dependent upon which outcome you're in. So let's do these one at a time. So for this one, for A, N times P, well, what's N? What's our sample size?
5.
160, right? We were told there was 160 students. Right? N is the sample size, guys.
Category.
Yeah, you were doing categories. So N is 160. So that's going to be, or should I'll just do it right here. So that's 160 times P, where for A's, we said the proportion is 0.25. So 160 times 0.25. That would give us 40. Do it again for part B, or for letter grade B. What's N? N is still 160. It's still a sample size of 160. What was the proportion for B? 0.25 as well. That's just coincidence. So again, we get 40. For C's, the sample size is still 160 students total. What is the proportion for C's? 0.4 or 0.40, right? We were told 40% for C's. That gives us 64. For D's, it's 160 times what? What's the proportion for D's? 0.05, because we were told 5% for D's, which is 8. And then F's was the same thing. F's was also 5%. So 160 N times 5% P is again 8. Any questions here, guys? Please, please, please stop me if you have a question. Remember, the goodness of fit test, this is the one where you actually have to do it by hand, okay? There's going to be multi-steps where we're filling it in by hand. Any questions? Okay. Are the criteria for chi-square distribution met? Yeah, right? Why? Because all our E values are greater than 5. Yes, because all expected values, which we just found are E's, are greater than 5. You guys okay here? Okay, let's continue. Complete the table to calculate the test statistic. Where do I get observed? Where do I get the O?
In the question.
Up there.
Yeah, that was provided. The observed is the sample data that was provided, right? This is from the teacher at the end of a randomly selected semester. They got the following grade distributions for the 160 student sample they got. So these here, this is our O. This is our observed data. So there were 42 A's, 36 B's, 60 C's, 14 D's, and 8 F's. The next column, the expected E, where do I get that from?
What we just found.
Yeah, that's what we just found in part B, right? That's what we just did in part B. So you're just bringing that over. For A's, we expected 40. We expected 40 B's. We expected 64 C's. Expected 8 D's and expected 8 F's. Next, we need to calculate the contributions for each outcome, the contributions for A's, B's, C, and so on. To calculate each of them, we use the following formula. We use the O minus E quantity squared divided by E. You have to do that each time, where we know our O, we know our E, so it's a matter of substitution. We shouldn't get any ugly decimals here, so we're just going to keep the decimals that we see, okay? So, do them one at a time. So we have 42 minus 40 quantity squared divided by 40. You should get 0.1. Okay, so you should get 0.1 for A. Next, for the B's, you have 36 minus 40 quantity squared, all divided by 40. You should get 0.4. Everyone okay here? Okay. Let's do it for the C's, which is 60 minus 64 quantity squared divided by 64, which is 0.25. Next, for the D's, you have 14 minus 8 quantity squared divided by 8. That is 4.5. And lastly, for the F's, 8. Oops. Yeah, it's going to be 0. I'm going to just finish out the whole process, though. 8 minus 8 quantity squared divided by 8 is 0. Yes.
On the B, for D, it's 160 times 0.05. It comes out to 80, but we're only writing down as 8.
I did that too, it's 0.5.
Oh, 0.05.
0.05, I was
Yeah.
using 0.
Yeah, 0.05. Yeah, careful with those zeros there. Any other questions? Is everyone okay with the table and how we filled in this table? Any questions? Okay, we're not done with part C though, because it also wants us to calculate the test statistic, to calculate this chi-squared down here. Does anyone recall how we do so?
We
We
add
add them up.
Yeah, you add up the contributions. You add up these values here. Add up the contributions. So 0.1 plus 0.4 plus 0.25 plus 4.5 plus 0. You should,
Can I write that up here, the sum?
It's right there.
It looks confusing, and I understand where it is. That's on the old one, but it's not on the new one.
but you could bring both formula sheets.
Can I just write it?
Mhm.
right now?
Yeah, that's fine.
Some of those.
Once you add them up, you should get 5.25. So we have our test statistic. Any questions up to here before I flip the page? All right. Next, what are the degrees of freedom? How do we calculate the degrees of freedom?
Categories minus 1.
Categories minus 1. How many categories you have or how many outcomes you have is another phrasing. Minus 1. There were 5 outcomes or 5 categories. It was A, B, C, D, or F. So you have 5 minus 1, which is 4. We can now calculate the p-value. Oops. All right, so the p-value equals chi-squared CDF. Remember, these are always right-tailed tests, right? Haven't we only been doing right-tailed tests for all of these sections? Yes. Okay, these are all right-tailed tests. So we have chi-squared CDF. The lower bound is your test statistic, which was 5.25. Since it's a right-tailed test, it goes towards positive infinity or 99999. And then the degrees of freedom, which we just found to be 4. So, do that in our calculators. Oops, I went too far. So I went to second distribution. Oh, let me start over. So I went to second distribution, go up to chi-squared CDF. Oh, there's a commercial on my screen. There it is. Okay, it's gone. Okay, so okay, so the lower bound was 5.25, and the upper is 99999, comma, the degrees of freedom was 4. And you should get, I'm going to go to 3 decimal places, 0.263. Yeah? 0.263? Very good. Part F. Or any questions? Does anyone need any calculator help? Yeah.
For that one, we put, which one's the first one? The 5.25. What is that?
The test statistic, the chi-squared test statistic, which we just found here by adding up all those contributions.
Okay. And then the last one's the degrees of freedom.
The degrees of freedom, yes. Any other questions? Okay, so what conclusions can you make about the null and alternative hypotheses? Well, our p-value is 26.3%, which, what was our level of significance? 1%. So 26.3% is not less than 1%, right? That makes it not statistically significant. So we do not reject the null and do not support the alternative. You guys okay with that? Okay. So now we can state our conclusion in the context of the problem, which is at a 1% significance level, the sample data do not support the claim that, the claim being your alternative hypotheses, but we want to be more specific here for our context of the problem. So it does not support the claim that the grade distribution, because remember, we were saying that the grade distribution in the alternative is not that we have 25% A, 25% B, 40% C, 5% D, and 5% F. Okay, so the sample data do not support the claim. What was the claim? The claim was that the grade distribution is not 25% A, 25% B, 25%, 40% C, 5% D, 5% F. We were saying that one of those was wrong, right? We were saying it wasn't that, but.
And so, just to clarify, we have to be this specific?
Yeah,
Okay.
yeah. Yeah, be this specific, guys. It needs to be in the context of the problem. Because if all you say is the sample data do not support the claim that the grade distribution above is not all correct. Well, it's like, well, what was that grade distribution? So I'm just recopying what the grade distribution
Wait,
was.
Can you go back?
Yeah.
The sample data do not support the claim. That the greatest-
Yeah. So the claim, sorry, 1 second. So the claim, the alternative hypothesis was that the grade distribution is not here. It's not these values.
But
And we're saying our sample data does not support that.
But aren't we, oh, we're not supporting, okay,
Yeah.
sorry.
No, you're good. You're good. Okay.
My
Question?
calculator, when you do X2 CDF, it takes me to this. I can't get out of it.
Okay, I need another minute here. Any questions here, guys? I mean, if it's helpful for you, another way you could have written the alternative is you could have said that, you could have said something here in the alternative that the grade distribution of A's being 25%, B's being 25%, C's being 40%, D's being 5%, F's being 5% is not correct, right? You could have been more explicit here,
Yeah.
right? You could have said that, you could have recopied this and said, these are not correct, okay?
Okay, do it without it totally confusing myself.
All right, so I'm going to stop the recording here, and then there'll be a new recording for the last two questions when we meet later on.